Alright, so today we're going to be talking about the alternating series test, and there's a couple things we want to keep in mind when we are using this test. The first thing, obviously, is that it can be only used in an alternating series, for example, -1 to the n over n, and it only tests for convergence. So if the alternating series test fails to test for convergence, you cannot assume that it's divergent. So the alternating series test is composed of two steps. And so, for example, if you had, this is just a generic series, a sub n, the first step would be to check that the limit as n goes to infinity of the absolute value of a sub n, so the part of the series that is not alternating, equals 0. So you want to make sure that that limit equals 0. And then the second step is to make sure that a sub n is a decreasing function. And that's the absolute value of a sub n. So for example, if you had a series like this, the a sub n, absolute value of a sub n equals 1 over n. So you would check that the limit of this function as n approaches infinity would equal 0. And you would also want to check that this is a decreasing function. Here's our next example. The series, starting at 0, going to infinity, of -1 to the n plus 1 times e to the 1 over n all over n. So our first step is going to take that non-alternating part, so ignoring the -1, and taking e to the 1 over n all over n, and we're going to take the limit of that as n goes to infinity, and it's going to be best to use L'Hopital's rule, so -1 over n squared times e to the 1 over n all over 1. We know that that's going to equal 0 because 1 over infinity is going to be 0. So that's the first step. The second step is going to be a little more complicated because we're going to have to use the derivative. So if we were to set our function equal to e to the 1 over x all over x, we could use f prime of x to see when the function is decreasing, and that's exactly what we want in the alternating series test. So we're going to have to use low d high minus high d low, draw a line square below. So it's going to be times e to the 1 over x minus 1 times e to the 1 over x all over x squared. We're going to get -1 over e to x times -1 over x minus 1, plus 1 actually. These are both positive because we factored out a negative here. That's all over x squared. And we know that that is going to be less than 0 whenever x is greater than 0. So we know that that function is decreasing. And because we specifically proved the two steps of the alternating series test, we can now say in our answer that the series of -1 to the n plus 1 times e to the 1 over n over n converges by the alternating series test, and you can use abbreviations if necessary. One last concept to talk about when you are using the alternating series test is finding the error in order to find the sum to the indicated accuracy. So here's an example where the question would ask, show the series is convergent. How many terms of the series do we need to add in order to find the sum to the indicated accuracy? So first thing you want to do is take that absolute value of a sub n and set it equal to the error to see which this error would be 5 over 10,000. In order to find at what nth term would you get the best accuracy. So, or this error. So you would take 1 over n to the 6 equal to 5 over 10,000. 5n to the 6 equals 10,000. And and n is going to be about 3.5495366. And what we can take from that is we can say that n equals 3 terms in order to get the indicated accuracy. So 3 terms is going to be your answer. Here's another good example to practice the alternating series test. We have the series starting at 1, going to infinity of -1 to the n times n to the 10 over n over 10 to the n. So our first step is going to be taking this part of it, ignoring the alternating part, taking the limit, and then we can use L'Hopital's to get ln of 10 times 10 to the n, and we know that that is going to be 0. So that's the first step. Second step, we're going to have to find out if this is decreasing. So an easy way is comparing it to the next term, n plus 1, and it's clear to see here that this denominator is going to be growing much faster than this one. And in terms of infinity, the n plus 1 is a very small change. So we know that this is going to be growing exponentially faster. So this is definitely going to be smaller. So we know that this function is decreasing. And then we can say that this series converges by the alternating series test.